Hey there, let's talk about chapter 14, which is on solutions. And for that discussion, let's head to the beach. Hey, wait a minute. Why are we going to go to the beach to talk about chemistry today? Glad you asked. Well, don't drink the seawater if you do go to the beach because that seawater has a high salt concentration, right? Makes it salt water. Well, you have some salt in your body cells. It's just a natural substance that we need. And the salt water would have a higher concentration than your cells have. And so when we have that scenario of two different solutions encountering each other, nature tends to want to equate those two solutions. And so what we'll have in order to do that in your body, the salt solution outside of your cells is going to pull water from your cells to it. And that causes your cells to dehydrate, which is not the way they're supposed to be. So you're going to have a pretty rough day. And also, there's a side effect of diarrhea with this. Because of that extra water that's come out of your cells, got to go somewhere. And so it usually ends up at the end of the digestive tract. Well, here's our composition of salt water. That's pretty gnarly wave there. Um, We've got our water molecules as we've always seen them, and our solute that's dissolved, in this case, is the ionic compound sodium chloride. And so we see that ionic compounds break apart or dissociate when mixed with water. All right, so then we get into these terms here. We have, let me see, I just moved my camera just a bit because of that definition there. So I have the majority component is called the solvent. We usually describe that as the substance that's doing the dissolving, and that's because it's usually the higher amount value, right? So we see the majority component being a quantity, comparing the two parts of a solution, but it's also what is doing the dissolving. Water is called the universal solvent because there are so many compounds that are able to dissolve in water. So if you just kind of remember that, water being the universal solvent, solvent is that role that water's playing. Okay, when you think about dissolving anything, Kool-Aid, whichever. Whichever's in the smaller quantity is called the solute, or what is dissolved. Okay, so these two parts together form a solution. So we found a tiny graphic there just to kind of help you visualize, right? Solvent is some liquid, solute is not always a solid, but it's what we're dissolving into. And then we get the mixture there you see as a solution. This is a mixture. This is not a chemical change. This is a physical change. Okay. All right. So here's a little bit more about what the seawater, going back to our beach intro, will do to your blood cells. So these are our red blood cells. If we look here on the right picture, that's our normal condition of the blood. They look kind of like a donut without the hole in the center. It looks as though it's rounded on the outer edges and really thin in the middle. That's our red blood cell carrying our oxygen and our carbon dioxide around our bloodstream. Well, the cell has a cellular border, a cell membrane, and that controls the movement of water, among other things, like our gases I just talked about. So if there's an unequal distribution around these cells of water, it's going to want to equate that between its surroundings and the inside. And so when we have salty water, there's more salt out here, so the water from the cells wants to come equate the salt level that's on the outside of the cell. And so that's why these cells are shriveled up. They're dehydrated, lost that water. And you can see how this shape is much different from the normal shape that we want. This shape is going to have a harder time moving through your blood vessels. See all those little spiky parts from being shriveled up? Just think of like a raisin. It's going to get caught on things inside your bloodstream. It's just not going to be a good afternoon for you. That's if you drink a lot of water at the beach. So, you accidentally get some in your mouth. It's not a big issue. I don't want to cause any alarm. All right. We have different mixtures, right? So this should be an overview from Chem 1. Homogeneous mixtures are a mixture, so it's not a chemical substance, not a pure substance. So it's two or more components together. The homogeneous refers to what it appears like. So the prefix homo in science means the same. So this means that these types of mixtures, they have the same appearance, or it appears as though it's only one thing. It's the same color and consistency throughout the container that you're observing. And so, for example, we have air. Yes, air is a mixture, right? They're not always liquids, even though that tends to be one of the more common examples that we talk about. But gases, right? In the room here with me, I have oxygen, I have some nitrogen, it's actually mostly nitrogen. I have carbon dioxide that I'm expelling right now as I'm talking to you, and a bunch of other gases just in smaller quantities. So that's a mixture. It's a homogeneous mixture because I can't see the different gases that make up that mixture. It all just looks like nothing, right? But I know they're there. And seawater is the same thing. So if we get a sample of seawater that does not contain seaweed or any other creatures, right, just the water, we would see that it looks just like another glass of water. Maybe slightly cloudy, but that's probably little critters floating around. So what I'm getting at is it looks as though it might be just regular water, but in fact, you know, coming from the ocean, it would be a high salt content. But it's a homogeneous mixture, okay? Let's take a look here on what this spontaneous mixing is. So what is that natural tendency of things? If we have a barrier between this container, say I have a large fish tank container, and there's a partition in the middle where we see here on the left as a barrier. And that's separating the two contents. I have a saltwater solution on the right, and I have just deionized water, pure water on the left. Now, if I remove that barrier and lift it up, so that it allows both solutions to integrate and mix with each other, what we're going to see is that it's going to spread throughout. And I don't have to do anything to force that. It's just a natural way that the ions are going to settle. And so this again is another example of our entropy, right? It goes towards disorder. Here's disorder. If things did not go as an increase in disorder naturally, they would remain as they are here with the barrier in place, right? So that's not how nature works, however. So back to our solvent and solute things. So in an aqueous solution, water is the solvent. What else is here? We've got some carbon dioxide molecules, right? And so we're taking a look at what appears to be some seltzer water, or perhaps it's a clear soda, and we know that it has bubbles. What are the bubbles? Well, in the factory, they inject some gas, and then they seal it up right away. And then it comes out to the store, and you buy it. So that carbonation there, that CO2, is locked inside of the liquid solution. And so once you release that uh, container by twisting the cap off, you hear that little psh noise. That's releasing the pressure that the CO2 is held under. And then you see it start to come out of solution as the bubbles. All right, so we've talked about solubility before in class, and here's where we're going to talk about it in more detail now in our chapter on solutions. So we're going to, we just did lab 3, where we talked about things that were soluble or insoluble. So we've covered the basis of solubility. Okay, so we can look at the definitions here and say, what does soluble mean? It means that they are able to mix within each other. And we use the term insoluble to mean that they are not able to mix. And so I have the picture there of oil and water, and you can see the chemical structures of both there. And so what does this depend on? Well, it depends on entropy, right? Nature's tendency towards mixing and the types of intermolecular forces at play, which is directly from our previous chapter. So here's a reminder of the intermolecular forces that we've encountered. So we have dispersion forces, which are found in every type of molecule. Okay, they're dominant in molecules that are not polar. So here we see just hydrogens and carbons on the left. So that's going to have just the dispersion forces present. We have then dipole-dipole. So we can see the oxygen in red there for this acetone molecule. This is nail polish remover, so you're probably familiar with that. And I hope you're not familiar with chloroform, the other molecule here, but it's used a lot in movies and such for kind of, over the cloth over someone's nose to kind of carry them away unwillingly. Um, so I hope you're not as familiar with that molecule, but here we are with the 3 chlorines on it. So the 3 chlorines of these green, it's going to pull the molecule downwards. Let me grab my molecule here. So it's the same as this one I've been using for a couple note sections now, right? It's a tetrahedral, but imagine that it's not just one green, that it's all of these 3 greens that I'm not holding, okay? And so to match with the notes, let me turn it that way. So we have it like this, and so you can see that the chlorines are stretching back. They're stretching away from the other side that I'm holding between my fingers here. They're pulling down. And so that's allowing what I am holding there, that little white hydrogen that you see in the picture as well, it's allowing that to be partially positive. And then the partial negative would be the other side of the molecule here with 3 chlorines. Okay. If I had 2 more green ones nearby, I would do that. But that would be chloroform. And so then we have the partial negative of our acetone attracting to that partial positive of the chloroform. That's the dipole-dipole. The hydrogen bonding is when we have 2 chemicals that are both highly polar, and they have the hydrogen attached to an electronegative element, so they're able to have this associative, sort of like a dipole-dipole, but it's stronger bond there, with hydrogens being partially positive and our oxygens of an adjacent molecule being partially negative, and that kind of magnetic attraction there between those 2. And then finally we have ion dipole, which is like our salt water. So this is what it looks like in solution. We have a sodium ion as part of our salt water. We'd have a chlorine somewhere else in our container. And that's the dissociation I talked about before of the sodium chloride. So when they dissociate, they're kind of floating around on their own now, and the water will surround them. And so in this case, we're looking at sodium, which is positive. It's not partial, it is positive. Okay, so it lost its electron there. And the oxygens are all partially negative for all of these water molecules that are in the solution. And so they align themselves so that that partial negative oxygen is facing the positive part of our cation, our sodium ion. Okay, so reviewing that, we have a couple more terms here. So the maximum amount of solute that can be dissolved in a given amount of solvent is a term called solubility, a property. And so we have a few terms here. So gases are always soluble in each other, like the gases in the room here with me, or wherever you are watching this. There's gas around you, and it's our oxygen, our nitrogen, our carbon dioxide, and a few others in smaller quantities, right? So they're all mixed together, even though we can't see them. 2 liquids that are both soluble are said to be miscible. So maybe you've heard that term before. So we could say alcohol and water are miscible with each other. They're able to mix. They become homogeneous. However, going back to that cartoon a few slides ago, oil and water are not miscible. So we wouldn't say not miscible. We would say immiscible is the proper term for that. So if they are able to mix, they are miscible. If they are not able to mix, they are immiscible. Okay? And so I have a star down here at the bottom. The solubility of one substance in another is going to vary with temperature and pressure. Can't get rid of those 2. All right, been seeing them a lot this semester. Okay, so I believe I mentioned this before Lab 3. Chemist's saying here is like dissolves like. And so what does that mean? It means that a chemical will dissolve in a solvent if it has a similar structure, meaning A polar solute will dissolve in a polar solvent. Nonpolar solute dissolves in a nonpolar solvent. So we have a little cartoon here, chemist humor. Polar bears are white, right? Any other bear would not be white. So we have help him dissolving. He's fallen off the iceberg there. And then the brown bear says, but bears are insoluble. And the white bear says, that's easy for you to say, you're not polar. Ah, he's dissolving in water. Okay. Hard to do the jokes when you're just sitting in your kitchen making a tape. All right, let's move on. So then we have a property, the heat of solution. I have a couple videos that you see pop up here. So just like other times, I'll post this presentation when I'm done with the video here, and you can go back to these slides and view these videos. Of course, I always try to find short videos that just get to the point, show you what I want you to be able to observe when talking about different topics. And so with this one, we have what's called the heat of solution. So when some compounds like sodium hydroxide uh, dissolve in water, a lot of heat is released. And so that first video is a demonstration of that. You'll see a thermometer and you'll see the red liquid in that thermometer. You'll visibly see it move up. Okay, we did this also in part in lab 3, and some of you noted to me that difference in temperature while you were holding the test tube. Another thing that's notable here is that sodium hydroxide, the NaOH, that's the same chemical that is in Drano that you use if you have pipes that the water is not draining properly, there's something stuck down there, whether it's grease from the kitchen or other, things that aren't supposed to be in the pipes, right? This happens as you use them. And so Drano, part of the way it works is that in water it releases heat. And so the idea is that heat will break down whatever gunk and grease could be clogging up that pipe in particular. So sometimes it works. Sometimes you need something stronger, but there you go. Down here we have other compounds like ammonium chloride. When that dissolves in water, heat's absorbed from the surroundings, and so the container itself gets cold. And this is a little trickier for students to comprehend, so definitely check out that video. I'm not going to give it away. You'll see, it's really cool. But here we go. Why do these two instances occur? Let's take a look what else we have in the slideshow. Okay, so we have the energetics of solution formation, or the enthalpy of solution. So let's kind of break down this topic. So this is not enthalpy of reaction, right? Because we're mixing now. We're not reacting. So to make a solution, we have 3 criteria. You have to separate the solute into its particles. And so it has to be endothermic to do that. We have to put energy in to break something apart. So the sodium chloride, that molecule, it's not bonded like my models are. What it is, see if I can hold these without obscuring them, right? So let's just say I have my positive white hydrogen here and I have my negative chlorine. So instead of table salt, we've got HCl, which is an acid. And so these two are they're positive ions and negative ions. They're just associating with each other like this. They're not physically bonded. They're just right next to each other because of those difference in charge. So they're just like magnets in a sense, staying together like that. But this is very strong attraction because it's not partial, it's full on positive and negative. So we're going to have to put energy in to separate these two. So keep that in mind, right? So that means it would be endothermic to do that. We're also going to need to separate the solvent molecules from each other in order for this mixture to occur. And so the solvent enthalpy has to be endothermic, right? Because we need to break stuff apart. We got to put energy in to do that. When we mix the solute and the solvent, now that they're broken up, we mix those components all together. That mixture is exothermic. It's releasing energy. So we can look at this said overall. The delta H for making a solution is going to depend on the magnitudes of the delta H's for these three processes. So which one is a larger number, that is for each component, and then we'll see who wins out of that math equation as to whether it will overall be exo or endo. All right, so here's just a graphic from the textbook about the solution process. So we'll go through each part. So we have a solute. They're represented by these red circles. Again, it doesn't have to be a solid. It could be a liquid. It could be a gas. But we have all the particles right next to each other. Let's say they're bonded because they're touching. We need to break them apart. And so the delta H of the solute has to be greater than 0. It has to be a positive number in order to break that particle that makes up the solute apart. To separate the solvent particles, we need to make room for the solute to mix and fit in, right? So we have the blue here. We have a liquid. There's more gaps between those blue particles on the left, and you can see how they're not ordered like a solid. They're kind of slouched on each other into, varied, arrangement, how they're kind of sitting there. But then as you see on the next one, the other beaker there after the arrow, we've almost lifted them up so that we had that extra space for our solute to fit in for this mixture. Okay, it's a huge exaggeration for that part. Okay, we don't really have it rising, but we have a positive delta H for our solvent. And then when we mix them, we're going to get a release of energy because things are settling down. And so if things are becoming more settled, they're becoming more organized in a way. I don't want to get into disorder per se, but here it's before we're mixing them together. Again, not a chemical reaction. And then afterwards, once they're contained together, our overall delta H of our mixture now will be a negative number, or exothermic. We'll keep discussing this, okay? So ion dipole, here's again where we're mixing our salt water, or I think in this one we're doing KF, so we have potassium fluoride here, 2 ions, and we're mixing them with water. And so when we dissolve them in water, we say it's hydrated. And this is the picture of both parts now. We saw earlier a sodium here surrounded by some waters. Here it's just a generic positive ion. And what would it look like for the negative ion? We have that picture down here. So the negative ion in the center, and you see the partial positive hydrogens of each water molecule now facing that negative ion. Okay, so that equilibrium stage, here's what we're talking about. So we have table salt in this example, NaCl, and you see it's a solid. And you have a little clock there by each beaker, just to say that time is progressing. Okay, so we have our salt, we drop it in, it's a solid, you can see the two parts, water and solid, very clearly. But then if we were to zoom in, the dissociation, or here they're saying dissolution, okay, of our sodium chloride crystal, it's starting to break apart. The sodiums and the chlorines are leaving each other. And look at our equation up here. Sodium chloride together as a solid, but as the ions, look at the state of matter change. It's now considered aqueous because it's in that water. Okay, so we've had a change of state shown here. Some more time goes by. Notice our original salt crystal is much, much smaller. And let me just pull my picture down so I'm not covering that. And so when we have the rate of dissolution equaling the rate of recrystallization, it's kind of going back and forth. Now, this is something that you're not going to really be able to witness. Okay, it's going to look as though it dissolves and then that's it. But imagine you let that container sit. You don't stir it anymore. So it just kind of sits on a table. And long amounts of period go by. This clock shows about 30 minutes. Let's say it stays there a few days, right? We can see the salt then come back out of the solution, and it would look as though we had the powder on the bottom of this container. And so that's when it recrystallizes out of the solution. So take a look at what we have up here in the middle beaker. As it was being pulled apart, we have an arrow just going to the right, showing that breaking apart of the ions. But then here we have a double-ended arrow, and that represents equilibrium. The same rate of forming the ions and then forming the solid again. So that's what equilibrium is. The reaction is still ongoing, not reaction, the um, interaction is still going on, but it's at the same rate. That's equilibrium. All right, so we have a limit. We have some terms here, 3 terms. And so when we have that dynamic equilibrium, dynamic just means it's still moving. So we have the formation of our solid and then the formation of our ions in aqueous solution, and that's still active, okay? And we have the maximum amount of solute where this can occur. We say that that solution is now saturated. That's the maximum solute that will dissolve. If I add any more, it's not going to dissolve. It's going to just sink to the bottom if it's more dense than the solution itself. Okay? If we could add more solute and still dissolve it, we would say our solution before doing that is unsaturated. And if we're able to force more solute to dissolve than it should, right? So if we, this is usually sugar solutions are the example here. So rock candy, if you've ever had rock candy, right? How is that made? They heat up a sugar solution. The heat helps the molecules move around faster. It's going to speed up the dissolving process, and it's going to allow you to dissolve more grams of sugar than you would at room temperature. And so then you would put, your stick for the rock candy, or if you had it on a string, you would suspend that in that sugar water solution. And then as that solution settles, as it starts to cool and everything calms down, you'll see the solid sugar recrystallize out because there was too much initially to be saturated. So it's super saturated, it starts to come out of solution, and that's how it deposits on the stick or the string to make rock candy. So that's my example there for you for supersaturated. Okay, so let's see. So solutions can be made saturated at non-room conditions, and they can allow, all right, so that's kind of what I'm talking about there with the supersaturated um, rock solution, uh, rock candy. Okay, and then down here, we can explain this little trick, right? Supersaturated solutions are unstable. They lose all the solute that's there over the saturation point when you disturb it. So shaking a carbonated beverage, okay, you're shaking around that CO2 in the soda that was saturated, supersaturated. And so then when you release the pressure by opening the can, it's all going to come out of solution and it comes out as that spray, right? So here we have, that looks like rock candy right there, just without the stick or the string. So one way that we would do this in chemistry that's the more practical way, other than making candy, which is kind of practical, right, is for us to isolate something that we know will crystallize out as a solid. So we know that we've created a mixture and the experiment's over, we were just heating it. And so in order to separate that mixture, instead of using like a funnel and filtering, we could do this method where we could just let the water evaporate and whatever's left would be just our solid that we wanted to isolate. All right, let's talk about temperature dependence. So gases, okay, have a lower solubility in water, so it's harder to dissolve the gases than an ionic or a polar covalent solid because most molecules are nonpolar, right? We have CO2. That's nonpolar. We have a carbon, 2 oxygens. There's no uneven pull with the electrons there, so CO2 is nonpolar. It's a linear molecule, nonpolar. All of our noble gases, those are nonpolar because there's no pull. It's just dispersion forces. So then we have gases with a high solubility are usually actually reacting with the water, not mixing. So that's a key point with gases. For all gases, the solubility is going to decrease as the temperature increases. So for gases and their solubility in a solvent, all you need to remember is that's an opposite relationship between the solubility and the temperature. So solubility goes down, temperature is up. Temperature goes down, solubility goes up. Okay, this is why soda is made and packaged under pressure under cold conditions. Okay, so we have the delta H of a solution is exothermic because you do not need to overcome solute-solute attractions in this case because we said the gases are typically non-polar. So here we have our soda. Okay, so for all gases, the solubility, I just copied and pasted this from the previous slide. The gas solubility will decrease as the temperature increases. So you can see that the bubbles in the cold soda pop are virtually non-present because they are dissolved in the soda. But if we have warm soda, we have a ton of bubbles because they're all coming out of solution. They're not staying dissolved in the soda. And so that's a perfect example right there. Cold soda, delish. All right, here's our first example. You should have the notes printed out for today. I've got a big box of equations there. That means we're going to have lots of fun in this chapter. So example 1 is right under there. This is a multiple choice question. Let's take a look. A solution is saturated in both nitrogen gas and solid potassium bromide, and we're at 75 degrees Celsius, pretty warm. When the solution is cooled to room temperature, again, that's 25 degrees C, what's most likely to happen? Take a second and think about that. All right, let's see what happens. Aha, our solid will precipitate out. So why is that? We have a star at the bottom there just to help you see why B is the correct answer. So the solubility of solids is going to be a direct relationship with temperature. And so the solubility is going to go down if the temperature goes down. So solubility, if it's down, means it's not staying in solution. So the potassium bromide was our solid here. As the temperature goes down, it's going to precipitate out of the solution or crystallize out. The solubility of gases, remember, is an opposite relationship with temperature. So the decreasing temperature coming to room temperature for the nitrogen, more nitrogen would actually dissolve in our solution. Okay, so here we have a soda can with our pressure. Okay, the larger the partial pressure of the gas. Okay, so perhaps you've talked about Dalton's law of partial pressures in Chem 1. It's a really easy equation. It's just where we take the pressure of each individual gas of that mixture and just add them together and get our total. So the partial pressure of a gas will contact with a liquid the more soluble the gas is in that liquid. And so we have our soda can as pressurized from the factory. We see a lot of the carbon dioxide there. Again, that linear molecule, nonpolar molecule. It's in solution. But then when you release that pressure by opening the tab, that's all your fizz coming out, those CO2 molecules just bursting out, carrying along a little bit of the soda on their backs as the spray that you see, right? And so we have the CO2 bubbles coming out of the solution there because of that release in pressure. All right, so that's our topic for solutions and making solutions and that sort of thing. We're going to stay kind of on the topic, but now talk about a different term, the term concentration. So the concentration refers to what's in there and how much of it is in there. And so this first statement, solutions have variable composition. They are not pure. They are mixtures. So I can make a mixture that is highly concentrated with a lot of solute, or I can make one with a lot of solvent and make it dilute. And so for the example here with these two terms, I like to use is Kool-Aid. And I may even be showing my age here, but I'm not sure if Kool-Aid still comes in the powders. I haven't been looking for it recently, but maybe you watching this can let me know when we see each other again. Does Kool-Aid still come in a powder, whether it's in one of those tubs, or I used to get them in a little paper pack that you'd rip open. Anyway, so if we make a solution of Kool-Aid, let's say we have some fruit punch Kool-Aid, and we mix it with water according to the directions, so it's just the way Kool-Aid Company intended you to make that refreshing beverage, that would be a concentrated solution. I have my solute, which is my Kool-Aid flavoring packet, and I have my solvent, the water, and it's dissolved according to the directions. It's concentrated. If I wanted to make that more watered down, I would add more water than the directions called for, and then I would have now a dilute Kool-Aid solution. So it's still a solution, it's a mixture, but I'm varying how much water and I'm varying how much of the Kool-Aid powder there is at any time. And so this is what we mean by it being variable composition. So the concentration is just a measurement of that solute for a given volume of solution. And there's different ways we can have this. The one that you've probably seen is molarity. That's the typical one that's taught in Chem 1. And that's what we, honestly, that's what we mostly use in the laboratory. You'll see for Lab 3 that we just completed, the sodium hydroxide and the hydrochloric acid were both 6 molar. That gives us information as to how much of that is liquid and how much of it is the aqueous component, whether it was the acid or the base. And so it tells you like how strong the solution is or how watered down it is. So 6 molar is moderately concentrated. They can go higher depending on the substance. So hydrochloric acid can go as high as 15, I believe. It may be 12. And the same with sodium hydroxide. So 6 is kind of in the midway point there between that and 0, so it's moderate. Okay. Molality has its own uses, and so you can see the difference in units there. And also keep an eye on what we're dividing by, right? So molarity is the entire solution. How much solute is in the overall solution? The solution is solute and solvent together. But look at molality here. It's the amount of solute per just the solvent, what's doing the dissolving, the water of our Kool-Aid solution. Okay, so we're just picking the 2 parts of our solution out and using those measurements to calculate molality. It's not really used that commonly anymore, but it has its place here and there. And then we have a mole fraction. So just as it sounds, we can look at how much of a particular solute that is in a solution with other solutes as well. And we could just say, okay, how much of this overall solution of many solutes is just this one particular solute? So we're almost isolating that. Notice there are no units for that. It's unitless because we have the moles canceling out. Okay, then we have a mole percent. So all we do there is we do the mole fraction equation and then times it by 100 and we get a percent. That's all it is. Okay, then we have part by mass. And so this can be a multiplication factor like parts per million or parts per billion. We'll talk about that in just a second, but that's part by mass. We have percent by mass. We would just multiply our previous calculation there by 100 to get it on a percent scale. That's a little easier to discuss in a lab report or talk about in general if that's something that you were studying. Here's our parts per million and parts per billion. You can see instead of multiplying by 100 to get the percent, we would multiply by the factor of a million, which is 10 to the 6th power, or billion, which is 10 to the 9th power. And lastly, we have parts by volume. We have the general equation here, and then our multiplication factor could be any of these that you see above there. All right, before we go any further, let's talk about the basics of making a solution. And so how do we do this? Well, first we would have to gather the materials we want, and that would be our solute. Let's just keep it simple and have one solute, and our solvent. And so I need to know how much solute I have to measure out, right? Let's say it's a solid. Let's say we have table salt, sodium chloride, and I want to make a salt solution. I need to know how much of the sodium chloride I need to measure out on a scoop and put on the balance in order to make the solution I want with that concentration. Okay, so the concentration is going to be my conversion factor. Take a look at what we can see here. If I want a 5% solution, then that means it's 5 grams if my solution overall is 100 grams. It's easiest to base things on 100 because that way you're not making these percents overly complicated. And so that's what we'll be seeing a lot of here. Okay, just going through the foundational motions of this calculation. And so what do we have here in quotes? Dissolve the grams of solute in enough solvent to total the total amount of solution. Yeah, that's a key statement there. So again, you want to note when it says the word solution versus the word solute or solvent, right? Solution is the entirety together. And so that requires, different thinking about what exactly you're calculating there. So just be careful of that. So here's how we prepare it. If we're going to prepare a solution to use in the lab, it's not just mixy-mixy. We have to do it a special way. So what we would do, here's our sodium chloride. So let's do 1 molar solution. That's easy enough. We could just add up the mass of sodium, which is 23.99 grams per mole, and the chlorine, which is 35. If we add those together, we get 58.44 grams per mole, and that's 1 mole. So just adding off the periodic table the components of our solute, we get 1 mole of that. So we put our solid in this volumetric flask. That's what these are called. They have a really thin neck, and you'll also notice there's a line somewhere on that flask, and it's on the neck, and that's the calibrated spot for that volumetric flask. So this one here, it looks like it's a 1 liter flask from what they're describing. You could have a 500 milliliter, which would be half this size. You could have a 2 liter. So they come all different sizes. You can have a 100 milliliter, a really tiny one. So it's all in what you want to make. So if we're making a liter solution, we're going to have our solid there that we measured for 1 mole. And then we're just going to fill the water up to that calibration mark on the glassware. And then we would just shake it or heat it to facilitate mixing. And then we would have our 1 molar sodium chloride solution. All right, so it says, this is from the textbook. This is not my disclaimer. A conceptual representation does not represent laboratory technique. Of course, we would go into safety protocols and things like that. I mean, it's a picture, okay? Okay, so we're going to go through each type, and we'll do a practice problem for each calculation. So make sure you've stretched, make sure your pencil's sharp. Here we go. So molarity is the moles of solute per 1 liter of solution. It describes how many molecules of solute are in each liter of solution. So let's break this down. Let's say we have sugar, right? We don't want to talk about salt all the time. So sugar. We have some sugar, and we're told the concentration is 2.0 molar. So what does that mean? It means we have 1 liter. That's the standard for our volume. Okay, so I have 1 liter of a sugar water solution, and I know that there are 2 moles of sugar floating around in there. Okay, I can also say that I have 2 liters. If I have 2 liters, then I must have double, 4 moles now, of the sugar, because that would be 4 moles over 2 liters. It would still reduce to a concentration equal to 2.0 molar. I can also go the other direction and say, oh, I only have half a liter here. And so if I have half a liter, I would need 1 mole of sugar, because 1 divided by half is equal to 2. So just think about all the different ways you could arrive at that concentration, right? I can make them all different ways, all different volumes, but still have that same concentration, that molarity that I'm looking for that particular solute. Okay, so there's our equation down at the bottom. We'll be using that the most. Here's our second example. Get your note packet ready. Here we go. A solution is prepared by mixing 1.00 grams of ethanol, which ethanol is a liquid, but because of density, we can measure the amount in grams of a liquid. Okay, so ethanol with 100 grams of water to give a final volume of 101 milliliters. Calculate the molarity of ethanol in this solution. So go ahead and take a minute, plug this into the molarity equation, and then bring the video back and we'll see how you did. All right, so this is how you should have arrived at your molarity for this problem. So we're always going to start with what we are given. We're given in this problem 1.00 grams of ethanol, so we're going to start our calculation with that value. Okay, we're going to then calculate how many grams are in that per mole. So we need to add up 2 carbons, 6 hydrogens, notice the formula, and 1 oxygen. And if we add up the mass for all of those elements, we're going to get 46.07 grams. Now, because we use the periodic table, that's always 1 mole when we do that. And so I'm transferring 1 gram using this ratio of molar mass to figure out how many moles of sugar are in just 1 gram. Okay, it would be 1 complete mole if I had 46 grams, but I only have 1 gram, so the amount of moles is much, much smaller. Make sense so far? So then we're going to deal with the other side, our solvent. Okay, we were told our whole solution here had a volume of 101 milliliters. Well, for molarity, we need to have the volume in liters to plug it into the molarity formula. So we're going to just convert. For every 1 liter, there are 1,000 milliliters. The prefix milli means 1,000. And so this problem just becomes moving the decimal place. And so instead of writing this conversion factor here for a liter and milliliter, if you feel comfortable with a metric system and that you know you're getting smaller by this calculation, you would know your decimal point is after that one on the right. To get smaller, I'd have to move the decimal point to the left. How do I know how many times to move it? Well, in this case, I'm dividing by 1,000, which has 3 zeros. So I would take my decimal point here, starting at the 1 on the right for 101, and move it 3 places to the left. So 1, 2, 3. And I would place my new decimal point right after that first one on the left of 101. And now look, here's my new value. So 101 milliliters would be equal to 0.101 liters. And just the same exact value, just described in a different unit. Now I can plug both those values into my molarity equation. So I do that, moles per liter, plug it in the calculator, you get an answer, and then you can leave it moles per liter. Or what we do is, as chemists, we usually use the capital letter M to stand for molarity. Okay, it looks close, but it's not. So this is molality. So we have molarity we just did. This is molality. And so like I said earlier, when we looked at the chart of all the different types of measurements, this one is not used that often anymore. But there are, some few and far between solutions that you would see with this measurement on it. And so this one we give the lowercase m. I know, we have 26 letters. We couldn't think of, using a few others. We just made it lowercase. Anywho, the moles of the solute per 1 kilogram of solvent. That's important. It's always per 1 kilogram of the solvent, not the entire solution like molarity was. Okay, so here we can see a star. So we have this type of solution will not vary with temperature because it's based on the mass, not the volume. So I guess that would be the the application where this would be useful. But like I said, we don't usually see this anymore. We usually see it just expressed as molarity and in experiments and literature and all that other stuff. But let's practice calculating molality. So you'll notice that this looks very familiar to the previous example, and that's because it is. It's the same values, but we're going to apply them to several different calculations here. So let's take a look at how this would come out. The same thing, 1 gram of ethanol, 100 grams of water, final volume of 101 milliliters, but we want molality. This is example 3. Go ahead and try it out, and then come back to the video and see how you did. Okay, so here we are. So we want moles of solute. Hey, we calculated that back in example 2, so we could just look back and see what that answer was. So we've got that from the previous example's work. But then we need kilograms of water, not our solution. So we have 100 grams of water given here. We're going to use that. We're not using the final volume of our total solution. The final volume here is ethanol and water together. Okay, but for finding molality, it's just the volume of our solvent, which in this case here is the water. So that's why we have just the 100 grams down here. And all we're doing is dividing it by 1,000 because a kilo is a larger unit, meaning 1,000. So we have a large unit of a kilogram, and 1,000 teeny little grams will fit inside there. So we're going to divide and move our decimal again. And when we do that, we end up with 0.217 molality of ethanol. All right. Oh boy, so now we're going to get a little nitty gritty here. So we have parts can be measured by mass or volume. We just talked about that. Parts are generally measured in the same units. So we could have parts by mass, which would be grams, kilograms, pounds, but we're going to stay away from the imperial system. And then we have milliliters and liters for volume, gallons again, we're not going to be doing that stuff here. And mass and volume combined in grams and milliliters together. So we have a couple things here. Again, you could see another YouTube video clip pop up if you wanted to see a different example of this calculation. I found this reference here, so you could check that out when you have this slideshow available after watching the video. But let's take a look at what else is on this slide here. So we have a percentage. A percentage of anything is how much per 100. Okay, that's a percent. Like your grades are how many points you got per 100%. And so, you know, how well did you do on that 100%? Instead of getting all of them correct, you've got 80 of them correct. Out of 100, you'd have an 80%, right? So here we could talk about with solutions. If a solution is 0.9% by mass, that tells me that there are 0.9 grams of solute for every 100 grams of solution. So we could think about the percent by mass as really a shorthand to write 0.9 grams of solute in every 100 grams of solution, right? So if you haven't figured out by now, us chemists, we're pretty lazy writers. And so, you know, we have elements here where we don't want to write the whole name. We write a 1, 2 letter, or sometimes 3-letter symbol, and then that's it. We don't want to write this whole phrase here, so we want to shorten it. And the way to do that in this case is percent by mass. Okay, we have others here. We have parts per million. So this is used a lot in environmental testing. If we were to test air samples of a location to see if there was a certain chemical that we did not want to find there, and we want to know what the concentration is. If it's a very low concentration that we're trying to measure, parts per million makes more sense to make that measurement than saying percent by mass, because the number would be so small. So if we're talking about really small things, it makes sense just to reference them in parts per million or parts per billion in that case. But application is usually environmental testing. We'll go to that video another time. Okay, so here's the parts per million. We abbreviate that ppm. So that's grams of solute per 1 million grams of the solution. Okay, so we have solution again, not solvent. I actually just thought of something that might be helpful to you all in keeping these straight, because I know not only are solution and then solvent used on these kind of rotationally, but solute and solution and solvent, they all start with S and they have O's and L's, and they're all very similar looking words. So as you're writing these down, perhaps you could try highlighting them in different colors. So I just thought of this. This isn't on a script or anything. So if I were you, what I would do is get a couple different highlighters. And for every equation that has the solution in the denominator, highlight those as one color. And for every one that has solvent as a denominator, highlight it in a different color. And so if you're a visual learner, particularly, you'll see that when you go to study, and perhaps your mind will be able to sort that better in remembering one versus another. But of course here, you don't have to memorize these formulas. They will be provided for you on quizzes and tests and so on. But putting some time in to get used to them and know what to expect certainly does make your life a little easier. So we'll just kind of leave it at that. Here's our parts per billion. Again, we see the multiplication factor there, 10 to the 9, where million was 10 to the 6th. All right, example 4, here we go. A solution is prepared. Wait a minute, I've read this before, right? Yep, it's that same exact question. We're just going through and calculating everything for this situation. So let's go ahead. 1.00 grams of ethanol, 100 grams of water, final volume's 101 mils. Calculate the mass percent. So let's do that. Take a minute, plug it in, come back, see how you did. All right, so here we go. So we have the mass of our ethanol and the mass of our total solution. Okay, our total solution was the 100 grams of water and the 1 gram of ethanol. And so we simplify this fraction and then multiply it by 100%. And so when we do that, we get 0.990% of ethanol, which is less than 1%, right? So mostly water. Okay, here's our example 5. What volume in milliliters, this is different now, of a soft drink? So we have a soda that's 10.5% sugar. 10.5% is kind of high. Okay. By mass, contains 78.5 grams of sucrose. Holy moly, that's a lot of sugar. So we're given the density of our sugar water solution is a little bit higher than the density of just pure water, which is at 1.04 grams per milliliter. So let's just kind of write out all the information that we were given there off to the side. There's a lot more to organize here. And we were asking for milliliters. Okay, so milliliters of our total solution. What do you think? Okay, so looking at this, we're going to use a couple different relationships here. So these are written off to the right. And so we want the percent by mass written as a ratio. So we have our mass of our sugar per mass of our total solution. And then we're going to need the density. And our density was given in grams per milliliter. So you want to make sure that you're showing that correctly for our calculation. And so we're always going to start with what is given. We are given 78.5 grams of sugar, so we're starting our calculation there. What do we want to do? Cancel that grams of sugar out. So we're going to have our percent by mass ratio next with our grams of sugar in the denominator, so they cancel out with our starting. And we're going to have grams of solution on top. So now that's our new unit. But we weren't asked to represent our answer in grams solution. We needed milliliters of solution. So that's where we need to use the density equation here for the sugar water solution in order to cancel out grams and go into milliliters. And so that was our setup. And when you multiply straight across in the denominator, simplify that fraction, we're going to get 719 milliliters of solution. That's quite a large soda. Okay, mole fraction. This one's not used that often either, so the only time you see it actually may be in this chapter. But let's talk about it. So mole fraction, instead of a fraction of a solution that we express as grams, where we can mass out, here we're talking about moles. Okay? So it may be calculated by the number of moles of one component present in the solution divided by the total moles of all chemical components. We can see some variables down here. We can look at the mole fraction of the solute alone. And so that would be, here we have x1. X is going to be what we represent mole fraction as. So that would be the moles, which is N, of our solute over the solution. And you notice it's the solute and solvent being added together here, N1 plus N2. And then I staggered the second part. I moved it over so that it wasn't too much lined up. I thought it would look confusing, so that's why this is over here. And so if we say the mole fraction of solvent, that's different, so it'll be an X2 then. The solute, we gave X1. So this would be N2. The 2 is referring to solvent, so the moles of solvent over the moles of our solution, our solute plus solvent together. And so when we add these two, right, one fraction, a second fraction, and those are the only two components of our solution, they should add up to equal one total solution, right? So this is useful in mole fractions. Here we are at example 6. So a solution is prepared by mixing 1.00 grams of ethanol with 100 grams of water to give that final volume of 101 milliliters. Calculate the mole fraction of ethanol for this solution. Try it out. All right, so here we go. So again, X is our symbol for mole fraction. And you can see this is a really fancy looking X, but that's how it may look in the textbook. So if you see that, that's what it means. And we just put of what we're solving the mole fraction for as a little subscript here. So we can see mole fraction of ethanol here. That's going to be my moles of ethanol over moles of ethanol plus moles of water. So we have to figure out how many moles of water there are before we can do this calculation. And we were given the grams of water in the problem, so we need to convert that into moles. And so to do that, we add up 2 hydrogens and 1 oxygen off the periodic table, and we get 18 grams for every 1 mole. That allows us to get rid of grams and get moles. And so how many moles of water do we have? We have 5.55 moles of water. Now we can plug it in. We have all the information we need. We have the moles that we calculated way back in the first example like this. I think it was example 2 that we did this, right? So we had our moles of ethanol already calculated. We just pull that. Then we're going to repeat it down in the denominator, but add it to the moles of water. And so when we simplify this, here's what we get. We get 0.00389. And here's a reminder, I did mention this earlier. Because this is a ratio, we had moles over moles. The moles are going to cancel. So mole fraction has no unit. The answer is just that number, 0.00389. All right, so to convert different units, you're going to start with what's given. You're going to write the concentration as a ratio. However, you need to flip it so that whatever the denominator is what you're canceling out your starting unit. You're going to separate the numerator and the denominator into the solute and the solution. You're going to convert both parts individually, right? So if we needed to convert our solute, like we did in this previous problem, let's go back. We had to convert our solvent alone here in grams. We had to convert it to moles. So we've separated that out of the calculation to do that off to the side. That's what we're talking about. And then we're plugging it in to our equation to solve for what we're asked for. Okay? So I know this is kind of wordy. Use the definitions, meaning the equations that we have, to calculate the new concentration unit. All right. So those are all the units that we're going to cover for concentration. The last bit of chapter 14 is talking about colligative properties. And so what are these? The definition is these are properties whose values depend only on the number of solute particles and not what the solute particles are made of. So it doesn't matter if it's polar, nonpolar, or whichever, it's just quantity. How much of that solute do you have there? Okay, so let's take a look at this. We have a few different examples of colligative properties, one being vapor pressure. So the vapor pressure of a solvent above a solution, so the pressure above a solution. So if we look at, I've got some Gatorade here, right? I like to have examples. Let me just pull the label quickly here. If I can get that corner so we can see a volume. And I'm going to cap it to be safe. Okay, I've got my Gatorade here. Okay, if you're wondering, this is the cucumber lime. I like it. I think it's good. Anyway, so this is the Gatorade, and we have our solvent, we'll say, for examples of what's on the screen, our level right here, but then we have air above it, right? And so that air is applying a pressure. Um, we're at normal conditions here, standard temperature and pressure, so we have about 1 atm pushing down on the surface of this liquid. And so we have the vapor pressure of a solvent above a solution is lower than the vapor pressure of the pure solvent. So we're comparing, if this were plain water, that would be a pure solvent, or a sugar water solution, which would be not pure, right? It's a mixture. And so the solute particles, when we mix those in, let's say we talk about sugar here, we're going to mix those in, and they're going to get in the way of our top layer of solvent. Sorry, I'm not in the camera there. Here we are. Got to get used to that. We have our layer here. And so when we mix in a solute, it's going to get in the way of the solvent that's there with this layer that's lining up with our air pressure. Okay? So here we go. So if I add a non-volatile solute, that's all we've been doing so far, so it's not changing anything. It's going to reduce the rate of vaporization because there's less solvent molecules up against the air in the container to evaporate. So it's like the solute is blocking them from releasing from the liquid phase into the gas phase. Okay, so we can see the solute here as red, and they're just kind of blocking the way. All right, so eventually we'll get equilibrium, but there's going to be a smaller number of vapor molecules, so the vapor pressure is going to be lower because that solute prevented more of the solvent from going into the vapor phase, so there's less vapor pressure. And so that's how it occurs. So the solute is blocking the solvent molecules from leaving. So then we have Raoult's law. So the vapor pressure of a volatile solvent. So volatile just means that under normal standard conditions, it has this relationship where it's going from liquid to gas without any added energy to it. So it's doing it almost spontaneously, we could think of, okay? So that's volatile. So we have a vapor pressure of a volatile solvent. So it wants to, on its own, go from liquid to gas and vapor. Above a solution that's equal to its normal vapor pressure, which we're going to signify with that small circle. So that's the normal vapor pressure of the substance if it were pure, multiplied by its mole fraction in that solution. Okay, so let's take a look at this equation. We have the vapor pressure of the solvent in the solution, and that's going to be equal to the mole fraction of our solvent times the solvent's vapor pressure if it were pure and not in solution. So that should make sense, right? The overall pressure of the solution is going to depend how much of it is there in the solution. So there's our mole fraction, right? That's a portion of it in the solution. Okay, so let's take a look at example 7. multiple choice question, but we have to do some thinking here to figure it out. Let me just bring my camera down a bit. Here we are. What is the vapor pressure of a solution in which the mole fraction of the solute is 0.200 and the vapor pressure of the pure solvent is 100.0 torr? And it says to assume that there's only one non-volatile, non-electrolyte solute. So it's not going to break apart like sodium chloride. Let's say we're talking about sugar here. Non-volatile, it's going to stay together as a sugar molecule and just mix into solution. So what do you think here? All right, so here we are. I'm going to move my camera away from that. The vapor pressure of a solution is that mole fraction of the solvent times the vapor pressure of the pure solvent. So we see the equation there, and what I did here was I lined up the equal signs so you could see how I've plugged it in. So we have the mole fraction of our solvent was given as 0.200, and we were given the pure solvent. So the language of this problem is what's really important, so that you place these in the appropriate location. That P with the little 0 sign, the degree symbol there, means that it's the pure solvent version. If it's in the solution, it's just the uppercase P. So that's a big difference, right? Having it on the other side of the equation or on the same side as the mole fraction. And so this just becomes a multiplication number, and we get A, 20 torr. We're jumping right into example 8. Here's a different problem. A solution contains 0.102 moles of calcium nitrate and 0.927 moles of water. Calculate the vapor pressure of the solution at 55 degrees Celsius. And we're given that the vapor pressure of pure water at the 55 degrees Celsius temperature is 118.1 torr. We're also told to assume that the calcium nitrate completely dissociates. So like table salt, this is an ionic compound. The calcium are going to break apart as cations with a +2 charge. And then the nitrates are going to stay together as NO3 with a -1 charge. And so it's going to split like that. And the water is going to surround it, just as you saw in the beginning of the discussion here, as it surrounds a positive ion versus a negative ion. It's going to look just the same. All right, so here we're going to organize our thoughts again because we have a lot going on in this problem. So what was given? We have that listed out here on the left, and what we're looking for the vapor pressure of the total solution. And so for this, we need to know how calcium nitrate breaks apart. Now, I was just discussing that, but I didn't discuss numbers, okay? Look at the formula here, CaNO3 2. So this is not a 1-to-1 ratio like sodium chloride was. That's really simple, just you get one of each. This is going to break apart with different ratios of cations to anions. So it says since 1 mole of calcium nitrate is going to break apart into 3 moles of dissolved particles, we're going to get 2 sodium nitrates, there it is, for every 1 calcium ion. So we get 3 particles. We're going to multiply the number of moles by 3 when we calculate that mole fraction. Okay, so it's because this is a complex formula that's not a 1-to-1 ratio of ions, we need to take into consideration how it's going to dissociate into ions, see how many ions we get from that, and that's going to be our multiplication factor in this type of problem. So let's see what that looks like. All I did was shrink the problem language up there. And so we have an ionic equation here to see how our calcium nitrate breaks apart. And there we are. There's our 2 nitrate ions that we saw from our original formula. That subscript 2 means we had 2 copies of our nitrate. And so that's our mole quantity of that ion. So now we're trying to figure out the fraction of water first, because we need that to figure out our solution. So we have our general formula here, the moles of water times 3 for our total particles here. I have 1 calcium ion for every 2 nitrates, so I have 3 particles dissolving, times the moles of the entire, sorry about that, the entire chemical, plus the moles times water, right? It's solute and solvent in the denominator. And so we figure this out, we plug in the numbers, we simplify, and then this number here gets plugged in with the normal vapor pressure for that solution. And so we have a multiplication here because of these symbols in the equation are multiplied. And so when we do that, we get 88.8 torr. That would be our vapor pressure of the solution. Okay, let's talk about lowering vapor pressure. So again, that vapor pressure of the solvent in a solution is always lower than the vapor pressure of the pure solvent. Because again, going back to the container, when we add something to a pure liquid, those added particles are now preventing the liquid solvent from escaping into the vapor phase. They're blocking them. They're just sitting along the surface, taking the place of other solvent molecules. So we have a mixed surface line here. And so that's going to lower the pressure because not as many particles from the solvent are able to go in the vapor phase as could if it were pure. Okay, so that's our situation. The vapor pressure of the solution is directly proportional to the amount of the solvent in the solution. So we have the difference between the vapor pressure of the pure solvent and the vapor pressure of the solvent in solution is called vapor pressure lowering. And so when we take the difference, we subtract. And here's our subtraction symbol here. So we have the change in, remember, we saw the delta all throughout the thermodynamics unit. The delta is the Greek letter for D, but in chemistry and science, it means the change in. So we're calculating the change in pressure. We have the pure pressure of the solvent minus the pressure of the solution. And we can then simplify that to the mole fraction and the pure solvent vapor pressure. Okay, what else is related to vapor pressure lowering? This will occur at all temperatures because, again, it's because of what you're mixing into that pure solvent. It's not really made dependent on temperature, it's what you're putting in there to block those solvent molecules. So what that means is the temperature is going to adjust. It's going to have to adjust to that blockage and it not being a pure solvent. So this results in the temperature to freeze a solution being lower than the freezing point of a pure solvent as well. And that brings us to freezing point depression or boiling point elevation. And so here we have a chart. There's a lot going on. You can go ahead and pause this and take a look at it in more detail later. But I have the picture here of some antifreeze being added to a car radiator. And so antifreeze is a solution of ethylene glycol, which is that neon green liquid you see coming out of there. It has a very sweet smell. And so because of that sweet smell, you really want to be careful not storing this around kids, or even some pets may be attracted to that smell because it is toxic. So side note. Otherwise, what it's going to do is it's going to lower the temperature that it has to be for water to freeze. Because we drive these cars year round, right? And especially here in the Northeast, it gets pretty cold in the winter. And you don't want your radiator, which is supposed to keep your engine cool by running the water around, right, to absorb that energy. We saw water had a high heat capacity. So the water goes around. Don't get me started on cars. The water goes around the engine components and absorbs the energy from those engine components as heat. The water takes that heat with it back to the radiator. It cools off because it's in the front of the car getting all that airflow. And then the cycle continues, pulling heat. So we can't just use water. You can in a pinch, but if it's very cold, you want to make sure to put antifreeze because that added ethylene glycol added to the water is going to make it so that the temperature outside has to be colder than freezing to freeze that solution because you want to be able to drive this car if the temperature is below freezing if you had to, right? So that's the theory behind that. So freezing point depression, of course we have a formula for this. Freezing point, okay, so we have our solution here. The difference between the freezing point of the solution and the freezing point of the pure solvent, you can see there we're doing FP for freezing point now, and you can see the added information there of solvent and solution. Then we have our change in freezing temperature. That's what this represents here. It's going to be our mass times, I'm sorry, the molar concentration. I don't know why I said mass, right? That would have been grams. Times our depression constant. And so this is a table depending on what the substance is. That's a different number to plug in. And then it tells us our units for this are going to be degrees Celsius per mole concentration, molality. Remember that? So that comes into play here for this calculation. And this is a lot here, right? There's a lot to be confused of because we're using a capital K in the formula, which does represent Kelvin other places, but here it's a degree Celsius. So just things to be mindful of, okay? You'll always be provided with these formulas, and I'll give a description as to what each component means. Okay, there's a video there. It's a short video. I'm going to let you see that on your own, but let's take a look quickly here at a reference table. So the KF is freezing, the KB is boiling point. So we can see the numbers here. The normal freezing point for benzene, which is a hydrocarbon, the normal freezing point is 5 degrees Celsius, 5.5, and then it's lowered when we have the freezing point factor. The normal boiling point is going to be 80 degrees, and then we see it much, much lower here at 2.3. So this is just kind of a table showing you different chemicals and how that relates, right? The normal freezing point of water is 0 degrees Celsius, but now it won't freeze until we have, temperature above 1. And then we have our normal boiling point. It boils at 100 degrees Celsius. Well, now, if I move my camera, we'd have the boiling factor now as 0.5. So let's see this in action. Calculate the freezing point of a 1.7 molality aqueous ethylene glycol solution, our antifreeze. I'm going to go ahead and put this all up on the board here. So let's talk through it. We're given a molality. We're asked to find the freezing point from its change. And so we're going to substitute into the equation, and we're going to calculate change in temperature freezing. So the actual freezing point is the freezing point of pure water, which would be the 0 degrees Celsius. We're going to have to subtract that from our change. And that way we can isolate the freezing point of this solution. So we're going to plug in the molality into our equation. We're going to plug in its factor from that table, and we're going to get a difference. But we're not done. To figure out the freezing point, we have to go from the original freezing point and see what the difference is. And so that's why we're doing this step down here. And so overall, we get our new freezing point at this molality of 1.7 to be negative 3.2 degrees C. Okay, boiling point elevation, we're almost done. So instead of freezing, now we're boiling. So we add components to our pure solvent, and it changes the temperature with which that solvent can boil. You see a very similar looking equation here. Let's take a look at example 10. Solution A is a 1.0 molality solution with a non-ionic solute. So it's going to stay together as a molecule, think sugar, and water as the solvent. Solution B is a 1.0 molality solution with the same non-ionic solute, but ethanol is the solvent, not water. Which solution has the greater increase in boiling point relative to its pure? So we're comparing ethanol and water. We may need to go back and reference the KB values for water and ethanol and compare them to their normal boiling point temperatures. So I'll give you a moment to give that some thought, and then we'll see what we get.